Okay, so let's get started. We're gonna talk about word embeddings today. Just some announcements. The fourth programming assignment is out and is due on the 13th. This is a Wednesday, I guess, 11:59 p.m. This is our last programming assignment. After that, you'll be working on your final project. So last time we were talking about language models as an example of RNN, and we saw that these are fundamental problems of natural language processing, so that's why we talk about them very often. And then we use them actually to discuss how we normally implement RNNs. We saw that Andrei Karpathy's implementation. Then I briefly talked about this problem of vanishing exploding gradients through time, because as the size of our sequences grow, the harder it is to train these networks, because it's hard to flow back the gradients to update the weight matrices with respect to the first time steps of the sequence. And then we saw that we can use more complicated networks or architectures to solve that problem. And in practice, LSTMs and GRUs, they let us process longer sequences. They're just more complicated ways of doing recurrency in a network. Okay, but theoretically, they process the same thing. They give an output at each time step. Just the way that they actually produce that output is a little bit more complicated. But theoretically, you can think about RNNs the same way. So for today, we're going to see, we're going to start talking about one-hot encoding and what are the problems of using one-hot encoding for processing sequences. Especially, we're going to focus here on words. So this is going to be focused, this lecture is going to be focused on processing text. Okay? And then to solve the problems you're going to see, we're going to propose or see this idea of word embeddings, which are just featurized representations of words. I'm going to show you some visualization, properties of these embeddings, and some applications, okay? And then we'll see two actually, I'm not going to talk about glove, but we're going to talk about two popular word embedding algorithms, okay? Word-to-vec and negative sampling. And we are not going to talk about debias word embeddings because we won't have time. Okay, that's the outline for today. So just a recap. So far we've been representing words using this encoding scheme called one-hot, where we have a vocabulary of words, which is defined down there, V, right, equals to A, Aaron, ... and then you have zebra, ... Zulu. We have all the words in the English vocabulary. And this is actually a simplification. And I'm assuming, for the sake of the arguments in this lecture, that our vocabulary has 10,000 words. Okay? In fact, it has actually much more. It has probably, we saw a text, last lecture, we saw that text file with almost 500K words. So this is an actual, even though it looks like a large vocabulary, it's actually a simplification of the real English vocabulary. So here are some examples, right? We have the words man, woman, king, queen, apple, and orange. And I'm actually showing in parentheses there their indices in this 10,000 word vocabulary, okay? Just remember that a one-hot encoded word is just this word full of zeros, or is a vector full of zeros, and just one dimension there is equal to 1. And for a given word, the dimension in parentheses is the dimension that is set to 1. Okay, so man here, the vector man there has 1 in the position 5,391. And I'm denoting for the sake of this lecture, whenever I use that notation O, a subscript 5,391, that's to denote the one-hot encoding of the word 5,391. Okay, so just as a short way of representing a one-hot notation. So when you see this little O there, just imagine this sparse vector that represents that word that has 1 in that position in the subscript. So woman is 9,853, and so on and so forth, right? So what is the problem, or the main problem with one-hot encoding for processing text? It's that it doesn't let the model, or any model, generalize across words really well. So for example, consider a language model that gives high probability to the sentence, I want a glass of orange juice, okay? So now consider that we're sampling from this model, with this context, a glass, I want a glass of apple, ... right? So for this model, apple and orange is as similar as apple and king, or apple and man, because the words, they have this very same distance, right? So there is no way for the model to know that apple and orange are somehow closer or more related than apple and king. I'm not saying one-hot encoding is useless, okay? I'm just saying that for processing words, especially natural language processing, is not the best idea. One-hot encoding is still useful. I mentioned whenever you have a categorical problem where categories don't have any relationship among them, actually one-hot encoding is the best thing to use, because you don't want to represent, or you don't want your vectors to actually have any particular or closer or longer distance from each other. Okay? But for text, it's not the best idea. And we will see some alternatives in this lecture. So the idea of word embeddings is to learn a featurized representation. So ideally, what we like to have is this featurized representation for words, where words with similar meaning, they have similar representation. Okay? So consider this table now. We have the same set of words there. And again, in parentheses, you still see there one-hot encoded values. But ideally, wouldn't it be nice if you could have, let's say, on the rows here, we have features for these words. So consider the feature gender, right? Then I would have, and assume these values, they go from -1 to 1. So wouldn't it be nice to have a representation where man has perhaps -1 for gender, woman has 1, and then king also has -0.95, which is closer to -1, and queen has closer to 1 values, 0.97. And then apple and oranges, because they're neutral values for gender, they should be close to 0, right? And then you could have another feature like royalty or something, right? And then for men and women, these words don't actually carry any information about royalty, so they should have like values 0s and 0s for royalty. But the words king and queen, they actually have higher values for royalty because those are royal words. So then you would have 0.93 or 0.95 for king and queen respectively. And same for apple and orange. They don't carry any meaning from royalty, so they should have 0s for this feature. And then the same for age and food and any other feature you would like to bring to the table here to represent words. Okay? So the intuition behind word embeddings is that we're going to learn representations that are going to have features in them. And we can learn actually any amount of features we want. The only problem is that we wouldn't know what these features mean. Okay? And we're going to see that along this lecture. Just for also simplicity, I'm going to use the word E to denote the embedding representation of a given word. So when you see E 5391, that's the embedding vector of the word man, or associated to the word man, which has the one-hot value of 5391. So for each of these words now, I have the E vector, which is the embedding vector. Okay? So now, look how apple and orange, they are much closer in the embedding space, right? If you compute the distance between apple and orange, now this distance is shorter than the distance between apple and king, for example. Okay. We can define the number of features you want to learn, but not what they actually represent. For example, I won't be able to say I want to learn gender values, I want to learn royal values, I want to learn age values. We wouldn't know what they represent, but we can configure the amount of rows, if you want, or amount of features in our learning problem. But as you will see, these word embeddings, they will give similar representations for words with similar meaning, right? And this is a really cool property of word embeddings. And because of that, they will allow our models to generalize across words much more easily. So for example, if you have that same problem of predicting the next word from the context, I want a glass of apple, ... Right? If my model had seen the sentence before, right, I want a glass of orange juice, then it would much easily now be able to predict that the word there is juice because it had seen before a sentence that is very similar, and now it knows it's similar because the vectors for orange and apple, they're very close to each other. So it will be much easier for the language model now to guess the word juice because of the embedding of these two words, okay? Does it make sense what I'm saying? Okay. Okay, so one popular thing to do with word embeddings is to visualize them using this algorithm called t-SNE, which is an algorithm by Hinton and his student, van der Marten. As you'll see, a lot of the ideas we are studying here comes from Jeff Hinton. So you can see how important he was, and he still is, for deep learning. But I'm not going to discuss the algorithm itself, right? But just for short, briefly, t-SNE, it learns a nonlinear mapping between the original representation, which is high dimensional. So assume, let's say we learned a word embedding of size 300. So we have 300 rows in that matrix. So 300 features we learned. We wouldn't be able to visualize this space. So one way you could visualize it is using this algorithm to project this to a 2D space now. And this algorithm is very cool because it learns this relationship or this mapping from this high dimensional space to this 2D space. And what you can see in these visualizations is, and this is a real visualization. I actually did this. The code will be linked on the website. This is not like a hypothetical thing. This is actually using word embeddings and actually using this algorithm, okay? So what you can see using t-SNE is that the word embeddings, they will group words of similar meaning together in this embedding space. So I think you can't read the words there, but here you have, let's say, words that represent numbers, so, or digits, right? 1, 2, 3, 4. So they will be very close together in this space. And here you would have the words representing fruits, apple, grape, orange. All right. Here, words that are related to royalty or royal families like king and queen. Here would be people, let's say woman and man. And here at the corner you would have dog, cat, and cow. Okay. What is interesting here is that look how cow is actually closer to apple, grape, and orange. They're closer to food than dog and cat. Okay, so you can think of this middle here as maybe like fruit stuff, right? So that's how maybe cow is closer to the fruits there. And also see how like words that are related to people in general are also closer together in space. Okay. So related to this proximity property, another interesting property of word embedding is that they allow you to do word analogies, and you can do that by solving vector arithmetic. So here I have the same table, exactly the same table. Now I'm just using like the subscript man, women, king, and so on instead of the numbers, because it's easier to see what's going on in the equations, okay? But when you see E-man is the embedding vector of the word man, right? And assume, if you want to imagine this in your head, you can think of a vector that is 300 by 1. Okay? So E man is 300 by 1. And so is E woman and E king and E queen. But now they are dense vectors. They're not sparse anymore. And you can imagine they have values from -1 to 1 in all these dimensions. Okay? So what you can do with word embeddings is solve word analogy problems. Like if you want to guess the word from the sentence man is to woman as king is to ... This is an analogy that we do in any language. Right? You can do that using the word embedding. And this is because if you subtract, for example, the embedding from king by the embedding of queen, you would get approximately -2000. And you can do the math there. You would get that result. Right? It's not going to be exact, that value, but it's just approximated value. And what is really cool is that if you do the same thing for men and women, you get a very similar result. Right? So the subtraction between E man minus E woman would be a very similar vector of the first subtraction. So you can visualize it this way. Here I have the vector from E man to E woman, right? So that's that vector here. This vector here is E man minus E woman, and this vector up here is E king minus E queen, right? So you'll see that they will be very similar vector. Here I'm showing they are exactly the same vectors. But what they will learn under the hood is this relationship of these words. So you can see that the subtraction somehow represents female, right? If you take a word and subtract that vector -2000, you would get the female version of a word. Let's say from man you would get woman, and from king you would have queen, right? Hopefully from he you should get she, and any example you can think of that should work. It's not 100% like that, right? In fact, when you look at the papers, they'll get a test set, and they'll show the accuracy of this problem. Say, for example, 70% of the words actually it guessed right doing this analogy problem. Okay, so not all the words it will get right, but it's surprising how many of these examples you can guess right just by playing with these vectors. Okay. So if you want to solve that problem for any particular example, let's say you can say Brasilia is to Brazil as Buenos Aires is to, right? Then you want to get Argentina. If you want to solve that problem, what you could do is you would get E Brazil minus E Brasilia minus E Brazil, right? And then you would solve this equation, right? On the other side, you would have Buenos Aires minus, then you don't know the word, right? The fourth word. So you need to solve this equation to find the word you're looking for, okay? And here, let's just for the sake of the example, let's just come back to this example you're seeing here. So if I want to find the word queen in that example, I would have to solve this equation, E man minus E woman equal to E king minus E question mark, right? So I can just solve this equation exactly. So I'm calling it EW the word that I'm looking for. That word is the word that maximizes the similarity between EW and the E king minus E man plus E woman. I just passed E woman to the right side. Okay, that's the simple thing. I just isolated this variable EW here. Okay. And if you do that, if you solve this problem, this maximization problem, then you actually get the word you're looking for. Okay. But how do you compute similarity, right? So computing similarity between vectors is a very important thing in deep learning. And there's many ways of doing that, but the most popular one is using cosine similarity, okay? And we haven't talked about this, probably some of you already know. this idea. But the cosine similarity between two vectors u and v is defined as this formula, which comes from the dot product. So similarity between u and v is the dot product of u and v divided by the magnitudes of these vectors multiplied. Okay, so what you're seeing there is the u, these two bars with the 2 at the bottom, just the L2 norm of u multiplied by the L2 norm of v, which is just the Euclidean norms that we normally use in geometric vectors. Okay. So this value, it ranges from -1 to 1. Okay, because we're normalizing the dot product. And if you remember from linear algebra, this is also this metric can be seen as the cosine of the angle between these two vectors. That's why the metric is called cosine similarity, right? So let's consider those two vectors u and v now. U is red and oh sorry, should be u and v down there. So the similarity between u and v is equal to the cosine of that angle phi. Okay? That's why the metric is called cosine similarity. And that's why it goes from -1 to 1. Because if you remember, the cosine function goes from -1 to 1. Right? And also from the cosine function, so if the angle between these two vectors is 0, then their cosine is 1, so the similarity between of them is 1. So think about this, right? If they're pointing at the same direction exactly, they're the same vector, and we have maximum similarity. And here we are disregarding the magnitudes of these vectors because we're normalizing them by their magnitudes. So this metric doesn't care about the magnitude of the vectors, only about the angle between them. Okay? So if they are pointing to the same direction, they're considered the same. So similarity maximum is 1. If they are orthogonal to each other, then cosine is 0, right? Cosine of 90 is 0. And you're going to have this 0 similarity, okay? And if they're pointing to the opposite directions, then their similarity will be -1. Okay. So this idea is used across deep learning in many different places. You're going to see this in different problems when you're in your career. It's good to know. There's other metrics of similarity. For instance, people also use just the dot product as a similarity metric without the normalization. It's another way of computing similarity. You wouldn't have the division by the norms because then you would consider the magnitude of the vectors as part of your metric. If you care about the size of your vector, then you can use just the dot product as your similarity. But if you get to a problem that's important, we're going to bring that discussion back. Okay? For now, let's just use similarity. And then you can think about similarity kind of as opposed to distance. Right? When you have a problem that you need to compare vectors, you could, in fact, use for example, the Euclidean distance between these two vectors as a distance metric. And then distance is the opposite of similarity. Right? This is the metric you could use to solve this problem. Right? Here. This similarity metric here is just the cosine similarity between these vectors. And so now you just have to find this word here that maximizes the similarity between with respect to this vector E king minus E man plus E woman. Simplest way to do that is just do a linear search on their vocabulary, right? And find the one that maximizes that value. Because we're going to change now to start talking about how we learn these things. And the first idea we need to understand is the embedding matrix. Okay? And that's the structure we use to learn word embeddings. So I'm going to just copy this to the board. I think it's easier to show this. A arrow dot 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 orange Zulu. Okay, and the word orange is 6,257. So, and you're going to have a matrix like this. I'm going to assume we want 300 dimensions for each word, and assume also that the size of our vocabulary is 10K. I have 10,000 words. So the words are represented in the columns, as we already were doing, and the rows represent features. I just don't know which row represents. Okay. And let's just keep the one-hot version of the word orange here, just so we can do an example. So the one-hot vector of the word orange would be full of zeros and have a 1 here, and then have a lot of zeros. And this, and the value 1 would be in the dimension 6,257. Okay, that's all you need to do to learn this matrix. And this matrix here is called the embedding matrix. Okay, we normally denote it as E. Okay, let me write it here actually. This is our embedding to this embedding matrix E. Okay. So what is the idea behind this matrix? I want to produce an embedding vector. I'm going to write it here. E, let's use that index 6,257. I want to produce an embedding vector by just multiplying this matrix with my O vector. That's the idea. This is a 10,000, 10K by 1 vector, right? And this is a 300 by 10K matrix. So I can multiply, on the left, I can multiply E by O. The effect of this multiplication is the following. Imagine this vector here transposed. What's going to happen when you multiply O, or E by O, you're going to see that each word that is not orange will have a weight of 0. And only the word orange will have the value 1. Or only this column orange here would have the value 1. And this will happen for all the rows. So essentially, because this is a one-hot vector, by doing this multiplication, I'm actually extracting this column from the table. It's literally like slicing this matrix and taking only this column. Okay, because this is one hot. Everything here will be 0, everything here will be 0. So I'll be left out with this vector here. That's why that's the E6257. This is the E6257 vector. Okay. Obviously, it's not going to be 1, right? What we're going to do is we're going to initialize this. This is a weight matrix. So we're going to initialize it randomly. So you're going to get some random values here. They're not ones, right? They're not ones here. They will be random values. But by doing this multiplication, you can just access a given column of this weight matrix. Is it clear? So that's it. That's what an embedding matrix is. It's just a matrix that we initialize randomly, and we multiply by one-hot vectors. And then we get these E vectors. And this E vector is going to be 300 by 1. And initially it will be random. But we want to learn this as part of a learning problem. Okay? Questions? Okay, so that's what I'm showing on the slide. So here is where it starts to get interesting. So there are many ways to actually learn an embedding matrix. But a very popular one, and perhaps one of the earliest ways of learning an embedding matrix, which was proposed here by Joshua Bengio in 2000 and others in 2003, right, in this paper, A Neuroprobabilistic Language Model, is to, the idea is very simple. You just add an embedding matrix before a neural network. Before processing the words, you add an embedding, what you call embedding layer. So look at the slides here. Consider the problem. It's a language model problem, right? So I have a context of 6 words, x1, x2, x3, x4, x5, and x6. And I want to predict the word x7 here. So one example could be, I want a glass of orange, and then I want to predict the word juice. Okay, so I want to train a model to predict this 7th word from a context of 6 words. What this approach does is it takes the words from the context, I want a glass of orange, so this is the context, and then just have their one-hot representations. And these representations are fed to an embedding matrix. Oh, sorry, this should be E. All of these should be E's. So you just feed the one-hot encoding or multiply by the embedding matrix, and note how it's the same embedding matrix for all the words. Okay, I'm not going to have different embedding matrix for different words. It's the same matrix E, right? I'm going to produce embedding vectors for each word, and I'm going to feed that instead of the one-hot encodings, I'm going to feed the embeddings to my network. This is a hidden layer. The green box there is a neural network. And it's interesting because it can be actually a feed-forward network or an RNN. It can be one of these two for now. And then you have, as an output layer, in blue there, you have a softmax layer that would have 10,000 output neurons because you have 10,000 words in the vocabulary, right? And you want to predict the word juice there. Okay? So the basic idea, we already had this from before, right? We already had the input layer in red using one-hot encoding. This is what you're actually doing in the assignment. There you're producing one-hot encodings for the characters. It's not words, but it's the same idea. And now, you also had the hidden layer here as an RNN, and the output was also a softmax. What we are adding here is this layer in the middle. All the rest is the same. Okay? And we are just literally just adding one matrix to our model, one E matrix. That's it. And surprisingly, if you train now a model that predicts the next word from a context, it learns a good embedding. So just think about this, right? We started the lecture discussing this problem. If my language model had already processed the sentence, I want a glass of apple juice, I wanted an embedding that would give a high probability to the sentence, I want a glass of apple juice, because those are exactly the same sentence. I just changed the fruit. So my language model should give high probabilities for both of the sentences, and the probabilities should be very similar. So intuitively, adding this embedding matrix would produce an embedding vectors that somehow help the model to predict the next word. So you would get a word embedding for words, in English in this case, that actually have those same properties we talked about. But again, this was very surprising, because this started to emerge very recently in history of natural language processing. Because people already had these ideas before, but I guess with the ability to process large quantities of text, then this word embeddings really started to show some practical, good practical results. As you just saw, the model is very simple, right? Okay, so just for generalization, you don't need to use a language model to learn embeddings. You can use other problems to learn embeddings. So when I say other problems, I'm talking about you can formulate the context and target in a different way. So if your goal is actually not to learn a language model and just the word embedding, you could have what we just did, which was like the context being the last K words, let's say last 4 words. I could, and the first row there is the language modeling approach. I want a glass of orange juice, so we have, in gray there we have the context of 4 words, and you predicting the word juice. But we could, differently, we could just have, for example, take the 4 words from the left and the 4 words from the right of a given word. Let's say if you have your target word still juice, but if you pick the 4 words on the left and 4 words on the right, that is an even more kind of complex context now that could provide you more information if you wanted. And you could do that. Nothing stops you to do that with text. Same just for last 1 word, or more surprisingly, if you pick a nearby word, just for example, if you have the word juice, you have a window of size 5, just pick a random word in this window that is close to your word, but it's not necessarily the last one. That's called skipgram. It's also a very good idea. Okay, so somehow you just need to create a context for a target word. And you can do that in many different ways because we are dealing with text. And we can get large corpus of text on the internet, and you could do that more or less easily. Okay. And that's what picking the words randomly is what word2vec does. Word2vec is a very popular word embedding model. And here I have this example. I want a glass of orange juice to drink with my cereal. That's just a longer sentence, so we can think about the word2vec model with an example in mind. And it learns a word embedding based on this idea of skipgrams. So I want to pick a word and some other word that is a neighbor of this word. And the idea of neighborhood is just a window of a certain size. And you can think of the size, for example, of 5. One way to imagine this would be maybe going to Wikipedia, just search UFV. You could download this article, pick a random word, right? Let's say agricultura, and then define a window of size 5. So now 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, right? And just pick any word in that window at random. So from the word, so agricultura is now our target, and we can pick, let's say, veterinária or escola or posteriormente as a context word. That's what word2vec does. So here I have the example orange as a context, sorry. I think I said differently, right? So we fix the context and we sample the target. Okay. So here I would get the context orange and I would sample neighbor words, juice, glass, my, from this window that is close to my word. And the goal of my learning problem is to predict the target from the context. And the model is pretty simple. In fact, it's even simpler than the one we saw in the previous slide. Here we don't even have that hidden layer in green. It's just a simple output layer. So this is just a softmax classification layer. Here I have one set of weights per word, that's it, where I'm denoting WT. So each target word has a given set of weights, W, and a bias value. But this is a softmax. What you're seeing here is a softmax formulation, right? We are modeling essentially the probability of the target word T given the context word C. And that's given by the softmax. So the equation you're seeing here is E to WE plus B over the sum from 1 to 10,000. So I'm summing the probabilities of each word. Okay? Great question. So the question is, like, we have same inputs with different outputs, right? And that's not, by definition, that's not a function, right? You have the same input given different outputs. So it is, in fact, very hard for the algorithm to maximize this or minimize this loss function. And here we're using the categorical cross-entropy loss function because of that reason. But our goal is not to actually use this predictor. Our goal is to use the embeddings that it's going to learn, right? And it actually learns really good embeddings just by doing that, okay? So basically, we're going to throw away the softmax and just pick the E at the end, okay? In practice, computing that probability is very expensive because we have to sum 10,000 terms at the bottom, and that's even a small vocabulary. In practice, you can have up to 1 million words, and that would be very inefficient. So in this paper, they actually talk about that. And they have a more complicated solution by having a hierarchical, like a hierarchy of classifiers. I don't want to talk about that because there is a much simpler solution, which is called negative sampling. So to deal with this problem of not having that softmax normalization at the bottom, that is a very long summation, we can do the following. So we're going to flip the problem a little bit. Before we had a multi-class, so in Word2Vec, we have a multi-class classification problem. That's why we have a softmax. But we're going to turn that into multiple binary classification problems. Okay? And the way you do that is similar. So we're going to think about the word orange just for now. We have that as a context. So we're going to sample one positive example using the skip gram approach. So you have a window, pick a neighbor word. For example, juice, right? And that's going to be label 1 because it's a positive example. It's a word that very likely is related to orange. And then you're going to sample other k random words to generate negative examples. Okay? So, but now you don't sample in your neighborhood, you just sample at random in your vocabulary. So you would get, for example, orange and king, orange and book, orange and the, orange and of, and they would be negative examples. So now you have a binary classification problem. You don't have more a multi-class classification problem. And that by itself solves the issue. You don't need the softmax anymore. And then you just change the model accordingly. What you do is you make one binary classifier for each word. And then you have, let's say, 10,000 binary classifiers. And I haven't mentioned it, but if you look at the bottom here, most of these works come from the same person, right? Mikolov. He was at Google back then. I don't know what he's doing now. But the Word2Vec, this model, many of these ideas of word embeddings come from this research lab. And he's the first author. In practice, when you're using word embeddings, there's two things you can do. Is either you go to the website of these models, let's say GloVe or or Word2Vec and grab their E matrices. They will provide to you an embedding matrix for the English vocabulary, for example. They pre-trained it in a very large data set of English text. So it's very beneficial for you if you're working with a very small data set to just take advantage of these embedding matrices that are already trained. So you can go, for instance, on their website, download it, and then you just plug that E matrix in your model. And the way you plug this E matrix is in between the input layer and the first hidden layer. Okay? If you look at any tutorial on PyTorch dealing with natural language processing these days, you'll see an embedding layer there. And what an embedding layer is doing is just initializing an embedding matrix. Let's see, embedding layer PyTorch. Here. This is, in PyTorch, this is the embedding layer. Let's see if there's an example here. Yeah, here is a 10 by 3 embedding layer. And this is, we don't have it here anymore, but would be a 10 rows by 3 words matrix, for example. So you just go here and add this embedding layer. Again, this makes sense for words, right? If you're working on the word level. In your assignment, you're working on a character level, then this doesn't make much sense, right? You already have a very small vocabulary for characters, and for characters, unless you want to learn if like vowels are should be closer to each other and consonants should be like closer to each other, then these ideas don't make much sense. But for words, this makes a lot of sense. So this is one approach. The other approach is to not actually initialize this matrix from a previous model. You can just initialize them randomly and let your learning procedure learn these matrices from scratch, from a random representation. Right? For example, in my PhD, I was working with music. Right? I couldn't reuse these matrices like from Word2Vec or anything like that. But I still added an embedding layer for processing my words. In my case, it would be like notes or music events. Right? So I still use these embeddings. I didn't do an analysis to understand what exactly the embeddings they were doing, but they tend to help minimizing the loss. Okay? Because they will, at the end of the day, they'll learn better representations for your inputs. Right? So in practice, whenever you're dealing with RNNs these days, you'll see any tutorial will have an embedding layer in the beginning. It's very rare to not use an embedding matrix these days. Okay? Because this is just a simple matrix that helps you learning better representations. And if you're lucky or if you have enough data, you can still get those nice properties, right? That we see in English and Portuguese and any other language, that those properties, they emerge. But if your sequences are not words, you might not get those nice properties. So it's not guaranteed that that would happen. First of all, it depends on the amount of data you have. It depends on the relationship between the words. So that idea is very clever. Word2Vec is very clever because the way the words are distributed in text, right? Words that are close to each other in the document, right? They're related in terms of meaning. So then you can do that trick of just sampling. It's very simple. Sample close nearby words, and you get a very nice embedding matrix. That might be the case in your sequential problem, right? But anyways, keep that in mind. This is a sentiment analysis example. Before we had just the input layer feeding the words as a sequence to the model. Now you would have an embedding matrix, and my hidden layer would be adjusted to take as input the embedding version of that one hot vector. Okay? So from now on, the hidden layer will process embeddings, and then the output would be based on the transformation of the embeddings itself. Right? This is normally how we use ORD embeddings. And as you'll see in the next couple of lectures, we're going to introduce, and perhaps I can move already my slides. In the next lecture, we're going to talk about attention mechanisms, which will build on top of embeddings. They are not necessarily directly related to embeddings at first place. But once you see attention, we'll see the transformer, which is based on attention. And the transformer is using attention to learn contextual embeddings. And that's very clever. Because right now, think about this, and I want just to leave you with this question for now. When we learn these embeddings, I'm going to go back to my first slide. When we learn these values, with word2vec, for example, and I finish the training, I have one fixed matrix, right? But there are words that, depending on their context, they should have different vectors. So, for instance, so the word apple, right? The word apple fruit and the word apple company, right? If my input sentence was I work at Apple, the word apple should have one vector. But if I had the sentence I am drinking an orange juice, or sorry, not orange, an apple juice, then the word apple has a different meaning. So the vector should be different. So I cannot represent embeddings with just a static matrix, right? Because depending on the context, this word should have a different vector. So in the next lectures, you'll see how transformers can do that. But before talking about transformers, we need to talk about attention on its own, and then we're going to get to that idea, okay? All right, thank you. I can take any questions now.